Okay, we're going to continue with our example. So we're analyzing the influence of the shear on the bending of a flat bar, which is the simplest case that we can consider, okay? So we have to integrate this qy dy over b. Now, here we just introduced the result from the previous calculation. See, we replace this into here, up to here, and we have dy. In this case, we are integrated from here to here, okay, and divided by b. Okay, so what we're going to calculate here is basically the, this will help us to calculate, see, more or less the calculation that we are doing right now is this, okay? So we are, see, not exactly, but it's proportional. See, we're saying that this deforms like this. So this is U at S, and this is U at 0. And basically, this difference is proportional to this amount here. Okay, so as we increase, we're going to increase this difference. Okay, if y equal to 0, okay, of course, it's the same value, so the difference is 0. Okay, so this is the integral that we have here. So we are able to calculate the second term. Okay, so this integral replaces this integral here. The other is just terms that which are basic: loading, yaw, shear, inertia. So we have this also. Now let's go now to the third one. And for this one, we need to calculate the total moment, okay, generated by this normal stress distribution, okay? And that normal moment, oh, okay, that's just replacing, this replaces into here. So this is the second term. This is this term here. Okay, now, let's go now to the third one. Okay, so this one here. So we need delta M, and delta M is the integration of all of these. Okay, but now we know that this term is the integral, which depends on y, has been already calculated. Okay, so this is delta M. Okay, this is similar, you remember, this is similar to the integration of the bending moment after we have done the assumption of the kinematic hypothesis. Okay, so it's sigma dy that give you a force, and we multiply by the arm, that's moment. But this moment produces something which tries to rotate in this direction. That's why we need the negative here. Okay, so we take all of this expression in here, and we know that this already was calculated. So let's do it. That's that. So dy is equal to b dy. All of this, it's sigma, including the negative here. So this negative here, let's see. As I said before, I warned you, we have to be careful with these negatives. Okay, so this negative is this one here. This negative comes from the previous slide. Okay, so that's it. This is sigma y dA. And we can recognize that there are certain terms which do not influence the integrand. So we have E, G, I, and E, G, and I. These are constants. P, remember, P depends on X. Okay, so it doesn't depend on any position of the section. So we can take that out of the integral. B is a constant. Y, that has to be part of the integration. And eventually, this is the result, okay? So here, you see that I have y cubed multiplied by one more, so that's y to the fourth. And if we integrate, we're going to get y to the fifth. That's the result, okay? This is an integration over the whole section, so we have to define this. This is y, so we go from here until here. That's why we go from minus h over 2 until h over 2. Okay, that's the total integrated over the whole section. So this is it's a value. Okay, please notice that before this integral depends on y. Okay, this is not, because it was integrated over the whole section. Okay, so this is not function of y. This is for the whole section. Now here, this p of x, of course, that's depends on x. So what we're saying is that this term here, delta m y over I, this term here will change as we analyze along the length of the beam. Okay, so that's not depends on x, but not it's a whole value for the whole section. Okay, rapidly we see that E and G have the same units. What are units of P? Anybody? Any units of little p? Units of little p, please. Let me ask somebody to participate. Mr. Sawai, what are units of P? What are units of P, Mr. Sawai? Units of P here?
Force over length.
Yes, force over length. Nice. So we have, let's here, let's change colors. We have force over length. We have B, that's length. We have H to the fifth, so it's length to the fifth here. Inertia in the denominator, Mrs. Sawai. Inertia.
The fourth.
Length to the fourth, yes. So we have 4 and 1, 5, cancels that, and we have moment. Okay? And now we have all the parts, we can put the whole thing together, and this is the result. Okay, so you see that you have some calculations with as function of y, but also as we go along the length of the beam, we have some influence, right? Because I see that I have the bending moment here, and that depends on x, and we also have p here, which also depends on x. So if we go along the length of the ship, the beam, there are some differences, but in general, the most important thing here is the dependence on y. Okay, and this is clear. So the dependence here, it's linear. The last term also is linear, and the intermediate term, it's cubic. So it's not in a straight line. There's some curvature there as we go up and down. So here, this is what we have, and we're going to include values. Okay, let's do this numerical. Okay, so the first is the expression again that we had before, and this table is in your class notes, people. You can follow from our class notes on page 46. Okay, so this is page 46 of your class notes. Okay, and these are the values that we're going to use. Okay, so we're going to consider a simply supported beam. So we're going to be like, this is the beam that we are analyzing. And we have uniform loading. This is equal to -5. Okay. Kilograms per centimeter. This is the thickness of the flat bar. Height is 20 centimeters, so it's strong. It's 20 centimeters. It's not a flat body, it's a piece of plate. The length is 1 meter. So it's a short beam, it's not very long. Similar to the one that we had in the laboratory. So we can calculate inertia. We have this term here. You see that it's the negative sign here. You have to be careful with this, okay? Because this is negative also. And we're going to evaluate here, okay, at the central part. Okay, so the bending moment is going to be something like this. Okay, so this is going to be the bending moment. Okay, and we're going to analyze at the central point, at the central section, and this is the value of the bending moment. So this is basically the value is going to be P0 L squared over 8, I think. You can do the calculations later, okay? This is also very important because at the end, remember that we're doing is that we're making a cut here, okay? And this is what we're doing. We make a cut, we have the reaction, okay? We have the force there. So this is the reaction as a force. So this is equal to P0 L over 2. This is P0. And here I have two values, right? And those two values are the shear force and the bending moment. That's the most important part. So I have this moment here. If I don't have this value exactly, I'm in trouble. Why? Because this is exactly the amount of bending moment that I need for equilibrium. Okay, now let's apply our formulations for this case. Okay. Now in this case, I'm sorry, I have you cannot see. Here, I apply the formulation for delta M that we had before, and this is the value that we obtained. Okay, so I replace this into here, and we can evaluate all of this expression. So this is the result of the evaluation. Okay, up here I have the three terms completely evaluated. Okay, so this is the bending moment, y over I. This is the integration of the shear correction. And this is delta M. Okay, delta M is equal to minus 520 y over I. So these and these terms are very similar. Okay, and this is the evaluation. Okay, so again, this is y. Okay. And in this direction, we have x. So we evaluated from down here for minus 10, and we got up until here. This is plus 10. Okay, so this is the integral that we recall that it depends on y. Let me write that down so we can improve our class notes. So that's a function of y. Okay, and we have this expression. We have this expression here. So see this expression here is this here. Okay, so yeah, when y equal to 0, this is 0. Now, this expression comes from here. Okay, so in the lower part, okay, here, y is minus 10. So we are here. Okay, I have to be careful here. So y is negative, this negative, and this negative produces a positive normal stress. And then we change linearly until the other side. Now, this is this. Okay, so this is h cubed. For h cubed, this is going to be, for the minimum, it's going to be positive. Yes, because this is larger than that one. Yeah. So that's positive with this negative. I have this negative. That's what we obtain. Okay, in this case, I'm evaluating only this part here without the negative sign. That's why I said this is minus. This is the Taylor correction. Okay, so for the lower part in this area, okay, the sign comes from the y. So that's the negative here, go to 0, then goes to positive side. Now this one here is equal to this plus this minus this. This is what you obtain. Okay, at the top, okay, instead of 187.5, you get 190.1. Okay, so that's not much of a difference, right? Because if you take 190, the percentage of difference is what about 2%? So it's a small difference, right? So it's not much, but in other cases it could be a little bit more important. Okay, so the difference, if you include or do not include the shear influence, is small in this case, and then we can go on and evaluate at any point that we want. Okay, so originally this is what we had. Now this is what we have for the normal stress, including the influence of the shear distortion. And finally, as we said before, we have to recuperate on this cut, on this section, the original bending moment, right? So the integration, and what we do here is we integrate using Simpson rule, and this thing here is the product. So this thing here is Simpson factor times y times sigma corrected. So which is this one here. One is minus 10. I'm sorry, it's minus 10 but this negative also. Yeah, because you integrate minus sigma y dA. Yes. So this is the summation, and this thing here is the summation. We multiply by the thickness, and then we multiply by delta y over 3. So in this case, delta y, as you can see here, it's 2 centimeters. And the result is 6250. And if we go back, what we can see it here is that the bending moment at the section was exactly the same value. Well, it's very close, right? So we have this value. So this is the bending moment. Okay. So this is not the original distribution, which is this one here, third column. We have a different normal stress distribution, but applying Taylor's assumption, Taylor's theory, we obtain a different, the same bending moment. Okay, using this correction from Engineer Taylor. Okay, is there any questions about this procedure, people? Any questions about this procedure? No? Okay, in this case, for tomorrow, please, I would like you to review on page 47. Please, everybody, open your class notes on page 47. Page 47, everybody. Page 47. Okay, there is another example. Okay, and this example is a little bit more complex. Okay, because it's a square section. Okay, and in this section we do the same procedure. Okay, so we go Q, but again we have to be careful because in this case we have to evaluate Q with a cut on the sides or on the webs if you want, right? And you integrate from there on all the way until the center line, which is symmetric. And also we have to do a second cut on the deck. Okay, so we have to be careful. Why? Because when we have to integrate in order to get this function, the integral of y, we integrate from 0, which is the neutral axis of reference, and you integrate up to 1 point. Okay, if this point ends in the side, okay, you have one value of Q. But you can also go on and integrate on the deck. Okay, in that case, you have to use the second one. Okay, so you have to be careful with this integration. Now, also, we have to be very careful because after that, we have to integrate the distribution of shear stress over the whole section. So we have to be careful because what we do is we integrate, since the section is symmetric, we can integrate from 0 until the top of the side. And then you continue, but with a different integral. But what you do is you evaluate at the top. And you said, okay, if I integrate from here to there, I have to use the result from the previous interval of integration. So you integrate over the whole section. Integrate from here to here, and that result you add to integration from the other part, from the deck. So it's just calculus, integral calculus, but we need to be careful with that, okay? And also, we have to be careful when you evaluate over the whole section, okay? You have some expression for the vertical sides and another expression for the decks or flanges, if you want, okay? This is example. And at the end, you have on the figure 214, page 51, okay? You have the distribution, okay, of the normal stress, distribution of normal stress, including the influence of the shear. And you can see immediately that in the connection between the vertical element, the sides, and the deck, on that point, you have an increment in stress, normal stress, okay? So in that point, we have to be a little bit careful, right? If you have that, okay, immediately now you could apply the concept of effective breath. You could apply effective breath concept and calculate the effective breath. But following this is a strong assumption engineer Taylor did. Very strong assumption. But we can obtain some values. In Muckle's book, okay, there is a nice explanation on this, but we're not going to go further, okay? But yeah, that's what we meant. We're going to insist on that. Even though the deck is at the constant distance from the neutral axis, on the deck, there is no constant normal stress distribution if you consider the shear stress. And finally, there is a comparison. I did a comparison using finite elements. And on figure 216, there is this comparison. We need to improve this because we apply a line force on the top of the side, and probably that put a lot of extra loading in that area. So we need to redo this. But in general, you see that the distributions are very close, except at the point where we have the application of the forces. So probably that's a cause, because we're applying concentrated forces in each one of these joints. So what we're saying, what I'm trying to say is that in general, we see that there is some good coincidence applying Taylor theory, even though it's a very assumption, a strong assumption based just in intuition. That's all. Okay. Is there any question? Please, you have to review this for tomorrow, because that's the topic for tomorrow. I'm thinking that if it is possible, if somebody wants to prepare a presentation, okay, and do the presentation instead of me, okay? So what I can do is you can explain this example, right, step by step, trying to not just to reproduce the class notes, but also to include some extra explanation, okay? That could be quite helpful. If there is a group that wants to do it, let me know, okay? I'm not going to give you extra credits for that, but I'm sure that's going to be quite useful for you. Okay, now, is there any problem with the assignment, which is due tomorrow? Group 1. Who is in group 1? Miss Santos, who is in your group?
Roger Carranza, Dairo, y
No,
Harry,
please.
Harry Cedeño.
Okay. How have you done any calculations? How far are you from completing?
We did the calculation for the effective breadth.
Okay.
From the time,
Okay.
effective breadth to time, but we obtain some like vibration like this.
It's not vibration, it's variation. Okay. That's fine. I'm glad. How about the other part, the shear stress calculation on the neutral axis? Did you calculate that too?
That part was calculated by Harry Cedeño, and
Okay.
he could explain us.
Mr. Cedeño, are you there? Mr. Cedeño?
Here, doctor.
Did you complete the calculation of the shear stress on the neutral axis?
Not yet. I'm trying to complete it.
Okay. Are you close or?
I'm seeing that the formula has the limitations because of the deformation of the, in the book says that.
No,
Can you
that's a
check?
limitation for this part here, not for the previous part. In the previous part, there's, I mean, some people don't like it, as I said before, because this formula originally was, okay. Remember, in chapter 1, we assumed that the only effect that they consider is bending moment, and they accept kinematic hypothesis. So they say, okay, two sections do this, right? So since this keeps straight, okay, the elongation here changes or varies in the y direction, varies linearly. Okay, so that's the result of that assumption. But then they take that assumption and go on in chapter 2, right? This is what we did. And eventually we just said that this section deforms. And this is the U that we have calculated. So at the beginning, in chapter 1, we said, this is what happens. We use that relation in order to deduce another one, which says that the section deforms actually. So that's what people don't like. But in general, it's acceptable. So there's no limitation. The limitation is in the Taylor theory. In Taylor theory, yes, we have a P of X. And if we have a concentrated force, we are in trouble. So don't worry, I'm not going to give you any concentrated force for this chapter. Okay, before we go on, Ms. Santos made a comment, okay? So this is what we have, okay? You receive, okay, files, so you obtain 2 files, okay? In one file, you have the strains. So you have the time here, and then we have epsilon x1 until epsilon x6. And in the other one, you have the force. Well, it's not really the force, right? It's the time in one column, and in the next one is the millivolts. And these millivolts are proportional to the force. Okay, this is what you obtain, right? So what you have to do is put both of these in a single Excel. This is what I did. So I have here, this is Excel. So here I have the time, I have millivolts. So with these millivolts, I can generate another column with a force in newtons. Okay, so these 2 columns from these 2 here. These 2 here comes in here. And then I took these 6 columns and bring it in here. Okay, and with these columns, I can take the first 3 or something like that, and I can calculate gamma xy, and I can calculate anything. And with the other 3, you can go on and calculate the effective breadth. Okay, now, what we can do is this, right? Since we have 1,000 values for every second, it's a large amount of information. So what you can do is this, okay? You can take, for example, how long did the test last? How many seconds did you have information for? Anybody remembers?
Like 20 seconds.
20 seconds. Okay, so we have here, you have 20 seconds. Okay, and that's multiplied by 1,000 points per second. So this is 20,000, about 20,000. Okay, so what we can do is we can take, for example, every 2 seconds. Okay, so this is the second, so that's about 2,000 values. Okay, for the 2,000 row, you can take these calculations. So you have one force, and you have calculated Here you have tau. And this is tau, you have theoretical using the force, and you have also experimental using epsilon and calculating gamma xy. And you can also have lambda over b, right? And then you take the same thing and you calculate for the next 2 seconds. So you have, this is the row 4000. Okay, and you do the same. And at the end, you have for this value, you have these results. For this value, you have these results. And you can plot for only for these values, you can plot the results if you want. Okay, but if you have done this calculation, it's easy just to copy the same formula in the first cell for the rest of the series. So it's up to you. Okay.
Doctor, I have a question.
Yeah.
All of the graphics have to be in like force versus time and tau versus time.
No, I don't think versus time is a good. It's a good choice. Okay, because there are 2 parts here. Okay, we have this formula for tau xy. And here we have the concept of effective breadth. So basically we have two curves that we need to see. So probably what I would do is I would put the force negative because since we have downward, this is negative. So if we change that, we can get positive. And tau, let's take the absolute value. Okay, and the relation, the theoretical relation is linear because this is equal to V Q over IB. And this is basically proportional to that. So the other are constants. So this is a line. And the other, I don't know, something like that. So this is the first one. And in the second one, something similar, right? So it's, you have force and you have lambda over B. So this is 1, okay? And you're gonna have something different for that, lower probably. Supposed to be a constant. This is a theory, DMV. And in experimental, I don't know what we are going to obtain. Okay. Also, it's a good idea if you present, for example, a graph like this. Okay, let's suppose this is the flange. Okay, so this is B. Okay, so more or less we have one value here, another value here, and another value here, more or less, right? So it's a good idea if you take some of these values and you plot it here. For example, for this one, you have normal stress, for a normal stress and a normal stress. Okay, and it'd be a good idea if you duplicate this on this side, you duplicate this on this side, and then you generate a curve like this. And you see that what we are doing, we are saying that even though the flange is at the constant vertical distance from neutral axis, you have a distribution of sigma, which is not uniform, not a constant. People, any question? Questions, people?
I want to be sure if there is just 2 values that are important in this report. I mean, the shear stresses and effective breadth. That's the 2 most important values in the report, or there's more?
Yes, those are the, see, remember, this is, you have to check the specific objectives. Okay, one is to check the formulation, and the other is the concept of effective breadth. Okay, and for one, that's why we employ these strain gauges on the neutral axis. And the other, that's why we use strain gauges on the flange. And the idea is that hopefully, I understand that you have this section like this, right? You apply the force, and the section was supposed to be doing something like this, going downward. But I understand that the force is not applied exactly in the vertical direction, and the section was not completely a very symmetric one. So probably there's going to be some torsion. It's difficult to avoid it, but let's try to do our best. Let's try to do our best. There is a question from Mr. Pesantes. Yes, Mr. Pesantes, you have a question?
Yes, doctor. I chatting with my parent. And we are discussion because well, okay. It is possible to change two activities, the assessment, the project, or the solve the lesson.
To change for what? The date?
Yeah.
And
Because
what day do you propose?
Sunday.
Sunday night? Okay.
I guess it's good for everyone because we have.
Okay. I can accept that. I can accept that. There is no problem.
Yes.
Yeah.
Thank you, doctor.
thank you so much.
Just a second. Sí, dígame. ¿Cómo? ¿A los qué? Pero ahorita no, porque estoy en clase. Denme 10 minutos. Ok, le cierro la puerta, por favor. I'm sorry. Yeah, no problem. Yeah, I'll move it for Sunday night. And tomorrow, if you have questions, bring them. Bring the questions for tomorrow.
Okay, doctor.
Good morning. I have a question. Sorry.
Yeah, go on.
I was checking, for example, in the case that when we have to, when we got the exactly value of effective breadth, experimental, and from TMB, okay, and we have something similar, we should have something similar. But then you told us the last class that we want to compare this value because we want to get a new inertia, and with that inertia, we can establish the maximum bending moment.
No, the maximum normal stress.
Normal stress.
Yeah.
And for example, in our case, we want similar, like you told before, compare with, for example, 5 or 6 values where the values are, how can I say that? Straight on or are near to the real effective breadth?
No, I know. I'm also doing the calculations, and I understand that there are some problems with the equipment that we employed. Especially, Engineer Isaac told me that the section, right, has some deformation, right? Now, if I take this, right, and I sit it on a completely flat surface, right? If I apply a force, this thing here will go downward. But the problem was that when you put the beam, right, on the foundation, on the supports, see, the lower flange was not horizontal, right? So there was some inclination, right? And you have to put something here in order to make this to be completely supported when we start. But if you have a section like this, I'm exaggerating. If you have a section like this and apply a force, you're going to have some torsion. And that prevents from getting, I mean, very close results with the theory. So yeah, we have to be flexible because we're going to have some problems in results, yes. But that's experimental.
And
Doctor.
If during the test, you observe something that you could think that we could improve this experiment, tell me, include it. So we could try to, if it makes sense, we could try to adjust our devices and try to improve next year.
Doctor, I have
just a second. Let me
okay.
go back to Benavides. Did I answer your concern? Okay.
Yeah, but I have another thing similar with that. Sorry.
Okay. So Hidro, please hold just a second, please. Let's go in order. Go
Yes,
on,
sir.
Benavides.
My question was okay, but for example, we want to compare the values, for example, in this case, with which one, for example, if we have the normal stress. For example, we want to make saying at the bending moment in the beam, get the maximum moment, and with the real value of TMB, we compare that value with the experimental to have something to compare.
Okay. Now here, what you have is effective breath versus force, right? If you apply DNV theory, right, implicitly, you are going to determine this value, right, because you have to reduce by this amount the effective breadth of the flange. Okay, so if you take this value here, you reduce this. Okay, so you reduce inertia. This is the mean value. So this is the value from pure bending theory, right? And for this, you use from here until here, full B. You apply DNV theory, so you don't take full B, but you take a percentage of B. That's the effective breadth, right? So you reduce inertia, and the result is going to get this value here automatically. And that's the concept of effective breadth. So you don't need to calculate this. If you apply DNV theory, this is what you are going to obtain. So you don't need to calculate sigma. What I'm asking you, this is just values that you can obtain using the epsilons that you measure. So this value here is not calculated, it's measured, because you take the strain multiplied by the Young modulus and you obtain that. So what I'm saying is that this is a good, for me, it is very important that you complete this chapter with the idea that when you have shear and you have a flange, there is going to be not uniform normal stress distribution, but there's going to be a variation. And this maximum value, that's important for us as designers, right? As designers, we need to be worried about the maximum value that we're going to develop, okay? So Benavides, I want the basic two graphs. One is the shear stress on the neutral axis, and the other is the effective breadth on the flange. The other graph that I show, it's very useful for you, just so you can physically see the distribution. You can see there is a maximum value at the connection between the web and the flange. Mr. Hidro, go on.
I wanted to say that me and my group used the two tests in this way. The first has no shear, so the second has shear in the position where the So we had the test number 2 to calculate the shear stresses, theoretical and experimental, and the first one to calculate the breadth. Is this a correct way to use these two tests, or we had to calculate the?
You're right. You're right in the sense
Okay.
that, okay, let me do this. Okay, let me change color. Let me try to draw here. In the case when you have a concentrated force in the center of the beam, in that case, in the positions where you have, okay, let me go back to the original color. So in blue, this is the situation in blue. You apply a force, you have a shear force in here, and this is where you measure all of this, right? Now, let me change now to green, okay? Now, in green, I'm still confused of which one is test 1 and test 2. We have this, half here, and you have the strains here. Now, in this case, there is no shear in this area, right? So what's going to be the shear stress here?
Theoretically 0.
Exactly. So you go like this. And I would like to see if we go experimental close to that. So you
Yes,
still need
yes.
to calculate.
We have to
Similar
calculate
here.
also that even if near to 0, or
Yes, that's what we expect, right? So let's see what the experiment says.
okay.
And for the second one, I don't remember your last name.
Hydro,
Hidro, what do you expect for the lambda over B in this case? That's a good question, right? When you have no shear, what's going to be the lambda over B ratio? The effectiveness.
lambda over B still there is normal stresses, so we can calculate that even in the two cases.
No. Okay, see, in this case, in this figure, you have this influence, this difference, I mean, this distribution, because we have the influence from the shear stress. Question for you, what would be the distribution of normal stress if there were no shear on this section? What would be the normal stress distribution? That's a good question, right? It would be like this. It will be like this. In this case, anybody, what would be the effective breadth in this case?
The result?
The flange,
What would be exactly? What would be the effective breadth? Come on.
the length of the
The
flange,
beam.
The beam. So what would be the effectiveness ratio? What
1.
would be this ratio?
1.
1. Yes. Who said that?
Hydro,
Okay, you got it, Didro. So in the second case, theoretically, is this, and experimentally, I don't know what you're going to obtain. Didro, are you with me?
yes.
Okay, so you have to calculate both cases. And one is extreme case when you have no shear effect. And the idea is that you see that when you have shear, that shear causes some differences from pure bending theory. And you have, when you don't have it, pure bending theory is good enough.
Also, I want to comment that because there's a lot of data and the two experiments, me and my group did this. we take a Python script. Well, we made a Python script and we uses the mean between. I mean 35,000 datas and we plot just the mean between.
No.
For example,
No. It's just too much. What you can do is you can take, for example, maybe 0.1 seconds. For example, take 10 values. 10 values, make an average of the force, of the millivolts, of the strains, and with that information, you go and do the calculation.
Yes, that the average.
But don't take too many points, because remember that in the test, the force was not constant. The force, see, you remember, right? You were, and every time the piston was going down. So if you take one measure here and another measure 0.01 seconds after that, the force has changed. So you cannot take too many points to make an average, because the force changes continuously. It's different if we make this test in another way. Okay, let's suppose we have the beam and we apply a weight and leave it there. In that case, the force is constant. So you still have a variation and you can take the average of that. That's correct. But not in this case, because in this case, the force is continuously increasing. So if you take an average of a very large interval, I don't know, it's going to be some problems. Okay? You can take the average, okay, but don't take it too long.
Okay.
As I said before, what you can do is you can split the information, right? If it's 20 seconds, you can split it, for example, in every 1 second or something like that. You can do the same thing using Excel. Excel is extremely useful. And what you can do is you can implement in one line your calculations. And then what you do is you simply take that formula and copy in the lower cells. And automatically, the values are updated for each one of the cells. You have to be careful, because when you take that cell and bring it down and copy down, some of the values has to be constant. Do you remember, if I do this, I implement a formula and I want to bring it down. Do you remember how can you make some values not to change in that formula? Do you remember?
The F4K.
Yes, you know it. So you put, for example, when you include the Young modulus, Shear modulus, Poisson ratio, the inertia, the thickness, things like that. So you can take those values fixed, and then you copy the formula. And of course, you have to accept that there's going to be a lot of variation, but this is experiment. Experiment, it's a lot of variation. Okay, let me go to, okay, if there's somebody, it's 9 and 10, okay, people. So if there is another question from Pesantes, let's make it quick because that's already 10 minutes over time. Mr. Pesante, you have any question?
Yes, doctor. In the book diagrams, the force is negative, of course.
Yeah.
Yeah, but the maximum shear stress is the sector in the 1 and the 2 sector, in the upper sector. Is okay, no?
Please. We are plotting, or we are comparing theory and experiment. Let me share. So where is located the shear, the
maximum shear stress?
No, that's, see, this is I'm drawing this with an extra height. Okay, I'm including in this area, I'm including the strain gauges. So in here is where I am going to calculate the shear stress. So if I see here, Okay, see this is x-axis, see? So you see this point here. So this is the sector that you want to calculate. This is your sector. And you have to consider this to calculate Q. Because in here, coincides with this, and with these three values, you can calculate gamma xy in this point. So this is the element that you are considering, right? So you are going to calculate, this is gamma xy, gamma yx that you are going to calculate using the elongations in x, in y, and at 45.
Yeah, but
see, the problem is that yes, you're right in the sense that in this point there is the maximum shear stress, but it is incorrect in the sense that we don't need to calculate there. We need to calculate there because in that position we have the strain gauges, and we are going to compare the values in that position, not because we have the maximum shear there.
Okay.
See, we need to consider that cut because in that point we have the strain gauges, right? So we are going to obtain in that point the shear strain, and with that we're going to go to shear stress and compare. That's the reason, because I could have included the gauges in the flange, right? And in that position, you don't have the maximum shear stress, but I want to compare. So you have to calculate the Q at the position where you want to compare the experiment and theory. In this case, yes, it is in the position where you have the maximum strain. That's why we put it in there.
Okay.
Santos, did I answer your concern?
Yep, thank you.
Okay, people. So tomorrow, please review this exercise. So everybody, so we can spend some time on that. And now at the end, we can spend some more time discussing about your experimental results. Unfortunately, I wanted to listen to, see, what we could do tomorrow is this, people, please. There is a responsible person for each group, right? So tomorrow, when I ask group 10 or 6 or whatever, immediately the person responsible in that group has to give me a quick report of how good you are in this work. I mean, I have completed the first part, I'm doing this, I'm doing that, and things like that. Or for example, what members of your group have cooperated? And he or she has to tell me, yeah, Mr. This, Mr. 2, this, that, and Miss this, did that. Okay, so you're responsible. That's why we elected you. Okay, people? I'm sorry it took me too much, but you have so many questions, and yeah, I would like to answer them. Okay, people, bye-bye now.